In this module, we will discuss the flight controls for the Fokker 100 and identify controls and indicators for primary and secondary flight controls located in the flight deck. This topic will focus on the primary flight controls and discuss how these control surfaces are trimmed. In normal operation, the topic will examine hydraulic operation of the flight control surfaces. In addition, we will examine autopilot, manual and alternate modes of operation.
The aileron control tab is normally not used. It is only unlocked in case the hydraulic actuator is depressurized, allowing tab control by the control wheel.
In the final section on malfunctions, we will discuss alerts and procedures associated with the primary flight controls. Secondary flight controls are dealt with in the next topic. The primary flight controls on the Fokker 100 include ailerons, the rudder, and the elevator. You will recall from an earlier module that both hydraulic systems 1 and 2 power the primary flight controls. The loss of a single hydraulic system does not therefore result in loss of primary flight control hydraulic operation.
Supplementary flight controls allow pitch trim through horizontal stabilizer adjustment. Aileron trim.
And rudder trim. In normal operation with the autopilot engaged, auxiliary flight control servo motors operate hydraulic actuators to control the elevator, ailerons, rudder, and horizontal stabilizer. With the autopilot disengaged, cables and levers transfer normal flight deck control inputs to the hydraulic actuators for control surface operation. A complete hydraulic failure requires manual operation of the elevators, ailerons, and rudder through cables and levers. The horizontal stabilizer is operated by an electric motor in the event of a complete hydraulic failure. We will discuss alternate operation of the primary flight controls later in this topic. Hydraulic actuation of all primary flight control surfaces is fundamentally the same. Control inputs direct hydraulic pressure to a hydraulic actuator by means of a pilot or servo valve. This causes either the actuator itself to move or the piston inside the actuator to move, and the control surface responds. The control surfaces respond according to flight control input with movement in one direction or the opposite direction. When control inputs stop, equilibrium is restored in the actuator, cutting off hydraulic pressure. As a result, movement of the control surface also ceases. Bypass valves are fitted in the actuators to prevent hydraulic lock should the actuators become depressurized. This arrangement ensures control is always maintained. If the pilot valve jams, a detent assembly switch detects the problem the next time a control input is attempted. This causes the bypass valves to open. A shut-off valve located upline of the actuator closes to remove hydraulic pressure if the system is turned off. The bypass valves open automatically to prevent hydraulic lock. Ailerons, rudder, and horizontal stabilizer are all fully powered. As a result, aerodynamic load on the control surfaces is not felt. An artificial feel mechanism is therefore incorporated in the ailerons and rudder controls. Load feel is proportional to the rate of flight control input and is not dependent on aircraft speed. Horizontal stabilizer adjustment provides pitch trim. No artificial feel is required in the stabilizer because aerodynamic load is always felt in the elevator mechanical system. The flight control lock prevents wind damage to the elevators and ailerons. The lock is located at the pedestal. The controls and indicators for the primary flight controls are located on the hydraulic panel at the overhead panel. We will describe each of the primary flight control systems individually, beginning with the elevator. The elevator consists of two surfaces hinged at the trailing edge of the horizontal stabilizer. The elevator has a range of movement from 25 degrees up to 15 degrees down. The two flight deck control columns that control elevator movement are interconnected under the flight deck floor by a torque tube. Both control columns act in unison. Two sets of cables transmit control column movement to the hydraulic actuators via cable tension regulators. These are mounted on a common shaft but operate independently to maintain correct tension in each cable. Autopilot servo motors and position transducers are also mounted on this shaft. The servo motors operate the elevator hydraulic actuators when an autopilot is engaged. In manual elevator operation, control column movements operate the elevator hydraulic actuators. The left actuator is powered by hydraulic system 1 and the right actuator is powered by hydraulic system 2. The ailerons are hinged on the outboard trailing edge of each wing. Aileron movement is up to 20 degrees in either direction. The ailerons move in opposite directions with no deflection differential. As one aileron is raised, the other is lowered by the same degree. Each aileron is fitted with an aileron control tab. These tabs are not aileron trim tabs. Their function is to augment aileron operation in the event of a hydraulic failure. The control wheels for the ailerons are interconnected by a control quadrant under the flight deck floor. From the control quadrant, a single cable transmits control wheel movement via a cable tension regulator to the aileron hydraulic actuators. With an autopilot engaged, commands from the autopilot servos operate the aileron hydraulic actuators. In automatic and manual control, the left aileron actuator receives hydraulic power from the number 1 system. The right actuator receives hydraulic power from number 2 system. An anti-upfloat cable connects the two ailerons, ensuring that aileron upfloat is prevented in the manual mode and that ailerons will remain synchronized in the event of a single hydraulic failure. Aileron trim is controlled by a knob on the center pedestal. The rudder is hinged at the trailing edge of the vertical stabilizer and has a range of movement of up to 33 degrees in either direction. The pilot's rudder pedals are connected to a control quadrant under the flight deck floor. A cable transfers movement to the two rudder actuators. These actuators receive their power separately from both hydraulic systems 1 and 2. In normal operations with both hydraulic systems functioning, number 2 system powers the number 2 actuator to operate the rudder. The number 1 actuator is depressurized.
AFCAS rudder servos are only used in redundant modes, for example, with dual autopilot engaged during takeoff and land Cat 2 or 3. During normal AFCAS operation, single autopilot or flight director, the yaw damper servos are used for turn coordination and Dutch roll damping. A rudder limiter reduces hydraulic pressure at the rudder actuator to prevent airframe stress during high speeds. Below 200 knots or with gear down, the rudder limiter ensures high pressure, 3000 psi, is supplied to the active hydraulic manifold. Above 200 knots, 1100 psi is supplied. It monitors system operation and ensures automatic changeover takes place in case of malfunctions.
The indicators for the rudder limiter are located at the flight augmentation panel. In normal operations, the rudder limiter push buttons are blank. Rudder trim is provided by a rudder trim wheel knob located at the pedestal. Adjustment of the entire horizontal stabilizer provides aircraft pitch trim, reducing aircraft drag. The Fokker 100 has 3 modes of stabilizer trim. With an autopilot engaged, auto trim adjustment commands come from the flight augmentation computer. Auto trim stabilizer adjustment reduces overall aircraft drag and prevents high pitch rates when the autopilot is disconnected. Auto trim requires hydraulic power. With both autopilots disconnected, manual trim commands can be made from the dual-element stabilizer trim switches. Manual trim inputs can also be made with the stabilizer trim wheel on the pedestal. Manual trim using control wheel switches and the pedestal trim wheel also require hydraulic power. Stabilizer trim inputs from the flight deck operate hydraulic actuators that power stabilizer movement. The horizontal stabilizer has 2 actuators. The left actuator is powered by hydraulic system 1 and the right by system 2. The position of the horizontal stabilizer is shown by an indicator at the central pedestal. The range of stabilizer movement is between 9 degrees aircraft nose up and 3 degrees aircraft nose down. The yellow off flag indicates a loss of signal or loss of AC electrical power to the indicator. In this instance, the pointer will be off scale. Horizontal stabilizer position is also indicated externally by markers on the vertical stabilizer for maintenance purposes. At speeds above Mach 0.75, with both autopilots off and no manual trim inputs, Mach trim becomes active. This trim mode uses Mach information to position the stabilizer.
If hydraulic power is lost, alternate trim using the alternate trim switch at the pedestal is available. We will discuss this mode of operation later in the module.
In this section, we will examine the operation of the primary flight controls. With the autopilot engaged, the flight controls are hydraulically operated by signals from the flight control computers and flight augmentation computer. If no autopilot is engaged, the primary flight controls are operated by conventional manual controls in the flight deck. Aileron trim is effected through adjusting the aileron trim wheel on the pedestal. Aileron trim adjusts the entire aileron surface. Locate the aileron trim wheel by touching it. Rotating the trim wheel clockwise raises the left wing. Rotating anti-clockwise raises the right wing. The trim knob remains in the last position set. Manual rudder operation is by means of rudder pedals connected to the rudder hydraulic actuators. Pedal position can be adjusted by cranking the pedal adjustment handles. Manual rudder trim is input from the rudder trim knob located at the main pedestal. Under normal operations with an autopilot engaged, rudder movement and trim is controlled by autopilot servos. You will recall that at high speeds, a rudder limiter prevents rapid movements at the rudder by reducing hydraulic pressure in the rudder actuator. The rudder limiter switch is located at the flight augmentation panel. The switch is dark in automatic mode.
In manual mode, low rudder system pressure is used for high speed, and high rudder system pressure is used for low speed.
With both autopilots disconnected, the horizontal stabilizer can be manually controlled by trim switches on the control columns. The trim switches control hydraulic actuators that move the stabilizer and remove elevator load. Both switches must be operated together. The dual-element switch guards against trim runaway in the event of a switch failure. The position of the horizontal stabilizer is shown on the indicator located on the pedestal. Touch the trim switches to move the stabilizer up 1 degree.
The stabilizer is now trimmed 3 degrees up, shown by the pointer on the stabilizer trim indicator.
Manual electrical trim and trim wheel operation of the horizontal stabilizer require hydraulic pressure availability. To conclude this section, we will examine the operation of the flight control lock located at the pedestal. The flight control lock is connected to the ailerons and elevator. The lock is set to prevent gust damage to ailerons and elevator. Raise the lever to lock the flight controls, and push the control column fully forward to lock the elevators. Finally, to unlock the flight controls, push the lever release knob up, and push the flight control lock lever down. In this section, we will examine the possible malfunctions associated with the primary flight controls and necessary procedures associated with such failures. Malfunctions are enunciated at the hydraulics panel, with the exception of the rudder limiter faults, which are enunciated at the flight augmentation panel. A single hydraulic failure for the elevator causes a level 1 alert. An amber message appears on the left MFDU. The right MFDU displays the corresponding message and procedure requiring the faulty system to be switched off. The faulty system displays a local fault light. This diagram shows when the alert for a single elevator hydraulic fault is inhibited. A double elevator hydraulic failure results in a level 2 alert and the appropriate procedure and alert at the MFDUs. Both the elevator push buttons show an amber fault light. Please take the necessary steps to cancel this alert. Now complete the procedure to remove the alert. Continue to cancel the alert. With both system push buttons pressed, only manual elevator operation is possible. An increased force is consequently felt at the controls. The alerts associated with a double elevator hydraulic failure are inhibited by the flight warning system between takeoff power and liftoff only. A single aileron hydraulic failure produces a level 1 alert. The relevant local light illuminates fault, and the MFDU displays the procedure to switch off the faulty system. The alert for a single aileron hydraulic failure is inhibited during the flight phases shown. Aileron servo tabs are fitted to each aileron to assist operation in the event of a hydraulic failure. The aileron servo for the affected aileron unlocks to augment manual aileron operation. If both aileron actuators fail, both aileron servo tabs unlock. Aileron control forces felt at the control wheel are significantly increased. Double aileron actuator failure causes a level 2 alert and the associated alert and procedures to appear at the MFDUs. Both aileron push buttons will indicate fault at the hydraulic panel. Pushing the aileron push buttons switches off both aileron hydraulic systems.
Manual operation of the ailerons is now required. Reduced aileron efficiency limits the maximum crosswind component to 15 knots.
The alert for a complete hydraulic failure is inhibited between 80 knots and liftoff. A single rudder hydraulic system failure and double rudder hydraulic system failure are enunciated by a level 1 and level 2 alert respectively, local fault lights and procedures at the MFDU. A double rudder hydraulic system failure also results in a stabilizer trim double channel fault, and a yaw damper double channel fault is indicated at the flight augmentation panel. Rudder limiter and yaw damper faults will also occur if the rudder channels are manually switched off. In both instances, the appropriate procedure at the MFDU should be applied. The alerts for a single and a double rudder hydraulic failure are inhibited during certain flight phases. A rudder limiter failure produces a level 1 alert, and the rudder limiter shows a fault. Pressing the rudder limiter push button selects manual control. In manual operation of the rudder limiter, high or low speed selections can be made. The rudder limiter speed push button will default to low if the landing gear is down and high if the landing gear is up. The speed push button is a toggle switch between high and low. Select the high speed mode. The rudder limiter is now operating at high speed mode. This mode allows a reduced hydraulic pressure to reach the rudder actuator, preventing rapid rudder movements and airframe stresses. Rudder limiter alerts are inhibited during the flight phases shown. A single system horizontal stabilizer fault produces a level 1 alert with the associated warning and procedure on the MFDUs and a local fault light. A double system failure results in a level 2 alert, MFDU message and procedure, and 2 local fault lights on the hydraulic panel. The alerts for a single and double horizontal stabilizer are inhibited during the flight phases shown.
After a total loss of hydraulic power, the alternate horizontal stabilizer switch located next to the trim wheel on the pedestal operates an electric motor.
The switch is pulled up to unlock it from the center position, pushed forward for aircraft nose down, or pulled back for aircraft nose up. When released, the switch is spring-loaded to the central neutral position. A jammed stabilizer will generate a level 2 alert, and the appropriate alert and procedure will be displayed at the MFDU. It is important that hydraulic power to the horizontal stabilizer actuator is not switched off. This prevents mechanical damage to the actuator. In the event of a jammed horizontal stabilizer, the procedure requires that you do not select stabilizer push button off at the hydraulics panel, do not operate the stabilizer trim wheel, and do not operate the alternate stabilizer trim switch. To prevent autopilot operation of the stabilizer, the stab trim push buttons at the flight augmentation panel should be selected off. The alert for a jammed stabilizer is inhibited between 80 knots and 400 feet at takeoff and during approach and landing. When landing with a jammed stabilizer, ensuring the jammed stab procedure has been completed, anticipate higher than normal elevator forces, maintain in-trim speed until starting approach, and use flaps at 25 for landing if runway length permits. In addition, establish landing configuration early, make thrust reductions in small steps, and finally start the flare slightly above the ref, avoiding prolonged hold-off. Finally, in this section, we will discuss abnormal control behavior when the rudder, ailerons, or elevator control progressively deteriorates. In the event of progressive deterioration in flight control behavior, simultaneously turn off the affected flight control hydraulic systems and check for improved behavior. If no improvement in control behavior is detected, switch both systems on again. In this topic, we have examined the primary flight controls and discussed their dependence on hydraulic pressure for normal operation. We have seen that the control surfaces are fully controlled by the autopilot and manually controlled when the autopilot is disengaged. And finally, we examined alternate operation of the primary flight controls, alerts and procedures generated as a result of failures, and dealt with abnormal control behavior.